membrane filtration. Very shortly, we will discuss some case studies where we make use of this to also repeat some of the knowledge we have gained and are going to be applied in the lecture overall. And we will finalize today's session with a short questionnaire to you, evaluation of this lecture. Let me share my transparencies. So please feel free to interrupt me anytime. If you have any questions, just talk in or write into the chat. Yeah, so we're finalizing the section where in the end we do have different types of enzyme mobilization discussed. And today we're still talking, finalizing filtration, membrane filtration. We have different integral and differential reactor operation. So if we're more in a plug flow mode or more in a CSTR mode, we have this thumb of rule. If we have a recirculation loop, which is 20 times faster than the direct flow, then we come close to a CSTR operation with a packed bed reactor. Then we discussed technologies, how to determine diffusion limitation. And remember, we talked about diffusion limitation, outer diffusion limitation. We talked about particle size determination and different technologies that we had discussed here in detail in the last 2 hours. Yeah, we stopped last week by pressure-driven membrane processes, meaning we do not now address any recirculation with any heterogenized biocatalyst or chemocatalyst with a catalyst is attached to surface. No, in this case, we're talking about homogeneously soluble biocatalyst macro polymers like proteins that are homogeneously soluble and are retained biospecific membrane. And the membranes we can dissect into these areas: filtration, microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. And they are differentiated in respect to the pressure difference that is generated by applying this technology, and they are, on the other hand, are subdivided because of the particular molecular sizes that are being retained. Until nanofiltration, everything's are pore membranes, meaning we have a flat sheet where we have defined pores of defined size. However, the size of the pores also do have a specific distribution and size, and therefore we do not have a real clear-cut separation particle or molecular size that's being retained. It depends also on the quality and generation of the membrane. In the reverse osmosis field, we do not have any pores. Here, the compounds need to be solubilized to the membrane. Now, we have two ways how we can operate this. One is so-named dead filtration. So that is, in the end, maybe used it already this morning, the coffee filter in your coffee machine, where you insert your particles, the coffee, grounded coffee, and those are just retained, and you just have a dead end filtration, so they are just retained by the membrane, and the liquid is passing through the membrane. In your coffee machine, it's extraction. Here, in our case, it is reaction. However, that is not a good way to do so, because large scale you will clog the membrane, you will observe strong biofouling, so formation of film layer on top of the membrane, and therefore we are also rather scaling up using a different way of operation. That is what you see on the right side, cross-flow operation. This means that the path of the liquid, the convection, is running parallel to the surface of the membrane. The difference is, because of this cross-flow operation, we do not form such a cake layer like what you see on the left side with dead end filtration, and the biofouling is lower or is less, because we have, with the liquid flux, we have shear forces on the surface maintaining the cake layer formation low. And then if you have your engineering knowledge in the back of your head, you might remember lectures on cleaning in place, so how to design the flux over any walls or in any tubes to have minimum amount of particles or material that is being deposited on the walls, and the same is true here. What is being retained that we are naming retentate, and filtrate that's passing through the membrane we name permeate. And we always have a pressure drop on the, if we compare retentate side to permeate side. So on the retentate side, so before the membrane, we always have a higher pressure. Now, how important point is, if we are coming back to this pressure process, is a question how efficient can we retain any particles or any molecules that are homogeneously solubilized with this area of ultra nanofiltration. Now, to determine this, we have a new term that is retention, what you see up here. Retention is abbreviated with the capital R, and it's a ratio of the concentration of the compound of interest in the permeate in relation to that of the retentate, and that is subtracted from 1. So we see here two ways now how we can determine the retention, and we differentiate the method of equilibrium-based and gravimetric determination. Equilibrium-based means that we have a filtration unit like what you see here, and the enzyme in our example homogeneously solubilized is mainly on the retentate side. This is the membrane, what you can see here. And now, however, it's not 100% retained, so we get some very small amount of enzymes that might be past the membrane. So now, equilibrium-based means we're pumping in a cycle over the membrane, so that after a defined time, we have an equilibration of those homogeneously solubilized macromolecules, which are being retained by the enzyme, by the membrane, in contrast to those that have passed. And now, if you draw a sample from the retentate side and you draw a sample from the permeate side, you determine the concentration. Then, at the end, you can calculate the retention. A different method is the so-named gravimetric method. There, we have a continuous flow operation of this membrane filtration unit, same macromolecules, same enzymes, homogeneously solubilized, retained by membrane. And now we're just withdrawing a sample out of the retentate side, measuring concentration, or alternative, and therefore gravimetric. Gravimetric means making use of mass balance, that we wait until we have reached steady state operation, and then we take out the whole volume from the retentate side, dry it, evaporate the solvent, and then we measure on a balance the amount of weight of the macromolecules that we have retained. Yeah, these are the two fundamental methods how to determine retentation. The important point is, residence time. So like down here, if you have a continuously operated reactor, we have residence time. Residence time was a ratio of volume of the reactor divided by the flux. And now we can run high number of residence times. So if we now pass high numbers of residence time to this reactors, you see here from 0 to 200, and continuous operation industry, we might even go to higher numbers. Then the question is, what is a good retention? And you see, if we have 99% retention of a specific compound, what sounds quite nice, it's really bad. Namely, after 50 residence times, we already have lost 40% of the compound. Even if we have 99%, so after 100 number of residence times, we almost have lost 8%. So in view of a valuable catalyst, you see we might even go to higher retention numbers, so 99.99, really have efficient operation. On the other hand, you also have to consider, if we're talking about enzyme, about thermic deactivation, which might also fit here in parallel, adding on to bad retention in view of residual activity that we can find in the reactor system. Now, how do such systems look like? So what we see here are centrifugal devices. So these are like small Eppendorf caps, and there you can insert the small beaker that you can see here, and at the end of this white residual part here, there's a filtration membrane, and no, sorry, it's here in the middle, in the white and the red part, and these are just typical commercial devices. So in the end, you fill in your retentate with a pipette on top of here. Then here is the filtration membrane, for example. Then you put it in a centrifuge, and by the gravimetric force, it will be pushed through the membrane, the liquid, and your proteins will be retentated here. And those are for centrifuges available for different sizes. But that's not good enough. Scaling up. And the point is, if you remember, we just discussed dead-end operation, cross-flow operation. So this is a typical example of a dead-end filtration. So if we're working in the lab, there's something what is named the Amicon stirred cell. What you can see here, they are available in different operation volumes, almost up to half a liter. And the minimum volume where it's operated with. The name Amicon cell is a bit like in Germany you talk about tempo tissues, but it's often not only from the company Tempo, but these were the ones who first brought this device on the market. In the end, how does it operate? We have a plexiglass cylinder that you can see here, and from the top there's a hanging stirrer, which has a magnet in here on the lower side. Below here is the membrane located, and here's the membrane located, and so below this device there we have a magnetic stirring device, so that from the bottom this stirrer is driven around. It's a dead-end filtration or cross-flow filtration, but because of the stirrer located so tight above the membrane, at least we have some flux over the membrane to prevent concentration polarization too strong on the membrane. And now to operate this efficient, so here's the outlet that comes below the membrane, and up here you can attach a nitrogen gas line, so that we can pressure enhance the filtration rate by gas pressure, and therefore this device is made in such a stainless steel or metal box to withstand the pressure. Maximum 75 psi operated, but still just small lab device, not good enough for scaling. For scaling, rather other devices are being used. What you can see here is a capillary membrane. So you can imagine this. You have like you have spaghettis, the noodle spaghetti standing in a glass. That's the same. This is a glass, and these are the noodles. These are the hollow fiber membranes, and the trick is they're glued in here in this top and also on the other side of that part, and through the membranes on this side entering we have the retentate, and here on the outside where you see the outlet here flowing around the membrane, that is the permeate. Now, next point is the other technology would be the tube and shell module, and this is in the end just thicker, with a thicker diameter, with a wider, more diameter membranes, where we can establish much higher fluxes than what you can see here in the hollow fiber membrane, and in consequence, this would be for scaling, but you have less surface area per reactor volume available, but much higher fluxes that are being possible. Yeah, and the last operation I would like to show you, this is really now large scale. You see a production hall. Here we have the ceramic filters as ultrafiltration membranes, and these are hollow ceramic plates that are stacked and on a spindle, and the spindle is turning at a high speed. And then we have different sections where vegetate and permeate can be separated as a rotating disc module with a very high convective flow on the surface to minimize fouling or concentration. Yeah, with this, we're at the end of this membrane section, so I hope I could give you a short overview how membrane filtration functions. I think that is enough what you need right now here for operation and of knowledge. Okay, then I will close this. What we're doing in the following is that we will now turn over to the case studies, and let me just switch the presentations. So you have what I have uploaded on the Step P. You have a large collection of different cases. Those are cases you can also go through just for practicing for the exam, for example. See if you can see the answers or come to the answers that are given there. The questions there are also typical questions we would like to ask you, or we're going to ask you during the written examination. And today I will just pick out just a couple of examples, and these I would really like to discuss with you. So it would be great if you would give any feedback either by in the chat, ask questions in the chat, or your feedback, or just open up your microphone, because what we're doing right now are for repetition, but typical examples like you will also have in the written exam, so it's your chance now to ask what you don't understand. And to do so, we're just walking through the different classifications of enzymes, and so we're starting up with oxiracases. So the first example I would like to show you is an example we already discussed in the Biocatalysis enzyme technology section. Remember, we discussed reduction of a decatone to the respective diol, and there are chemical methods. There are chemical methods like with ruthenium bina, chemocatalysis, molecular hydrogen to carry out this non-selective reduction that you can see here. The product out of the chemo reduction yields 70% DE, diastematic excess, and 86% EE. If you do not know how EE or DE is defined, look it up into the older lectures. Now, what we're discussing right now is making use of cells, whole cells from Lactobacillus kefir. Some of you might even like Lactobacillus kefir because you can buy it in the supermarket, and maybe some of you even have drunk it this morning. Now, these cells can directly be used to carry out this reduction, and the beauty of the biotransformation is we can do this with 99.5% 90 DE and 99.5% E. So much better than any chemocatalytic reaction. Now, from the Biocatalysis enzyme technology lecture, you know this will be a two-step reaction because we have two functional groups. These two functional groups will be reduced in subsequent 2 steps. And now the redox equivalents, that's nicotinamide cofactors, but it's integrated in the cell, so we don't need to care for cofactor regeneration because it's part of the whole metabolism of the whole cell that's being active here. However, we need to supply a co-substrate, and that would be, in this case, glucose. Yeah, and side products are lactate. Okay, let's run this batch. Now, we see here a batch operation, and it's typical what you would expect. So we have the starting material, diketone, decrease as function of time. We have B, the hydrox ketone being formed as intermediate, and which is then later on reduced by time by setting up the final product. So it almost looks perfect. Yeah? So we have larger 99.5% E, larger 99.5% DE. We have complete conversion. And if we look at the reaction conditions, we have 22 grams of bio-dry mass per liter of the lactobacillus kefir cells. We have 130 millimolar limit excess of the glucose in relation to the starting material 110 millimolar hexanedione, pH 6 30 degrees. Now, excellent, I would say. Couldn't be better, one would think. But it's not the case because the productivity is really bad. We're just producing half a gram of product, or approximately half a gram of product per gram of cell. So that's not really efficient. And the question now is, how can we increase the productivity per experiment? In this case, productivity to make more use of the cells. Now, I would be happy to take any suggestions from you. Either open up your microphone or just write into the chat. No one? Stripping away side product. Well, lactate, it's an acid that's soluble. There's nothing that you can strip. And we want to increase the amount of product we can produce per amount of cell that is in this batch reactor, the tank reactor.
The problem looks like one that we already had, where the product B was being precipitated, or it was sort of crystallizing out and then resolubilizing and then reacting on to C. Is it the same problem here?
No, because what you see from the course, so A, diketone is totally consumed. That's intermediate being formed and there's nothing crystallizing, and the final product is also soluble. So we just want to produce more of this in relation to the cells that we insert into this reactor. If we want to produce more of the product, we need to add more of the starting material to the reactor. And so we would need to think about reactor technologies that we can apply here. And this brings us back to what we discussed in the lecture: batch and continuously operated reactor. Now we are working with this tank reactor, and the second simplest we can think of is that we run a fed batch. So the reactor we just had, where we just have a constant stream added to the reactor of glucose and hexanedione. Okay. Now you see this looks really quite nice, and our target product C is 100% formed with high DE. And now thinking about how to increase productivity, we decided most easy would not to be setting up a continuous operated tank reactor. We just fetch out of our storage a pump and add this to our reactor. and then operate a fed batch. And hopefully we can see constant product formation. Okay, so let's do an experiment, and I show you the first experiment we're running. This is the experiment. So we're starting up with a feed of 24 millimole per hour. Now, A is feed the glucose plus the hexanedione in the specific ratio is fed to this rate. But now the strange thing is, everything looks different what we have expected. Major product is our intermediate B, and C is a minor compound. What did we do wrong? How can we optimize this? Because the batch that was ideal was just the productivity was not high enough. Therefore, we wanted to add more starting material, and suddenly performance is more than bad. What did we do wrong, and how can we optimize it? Any ideas? If you look, the answer is directly shown on the transparency. So what do you observe, or what do you notice if you look at the courses of the compounds A, B, and C?
The B doesn't react fast enough to.
Can you speak a little bit louder? Sorry.
Intermediate B does not react fast enough to generate C. The second reaction constant is.
That is right. If not fast enough, I do not know. But yeah, in the end, what could be the reason?
Maybe substrate inhibition? Sorry?
No, you see, the answer is directly on the transparency. We don't have any information on kinetics now, and I don't give you any information on kinetics because the answer is directly shown in front of you. So I introduce this transparency that we have a feed rate of A, that's the starting material in the sequence of the diketone, 24 millimole per hour. Yeah. So what do you see in this plot? If you're looking, what does this curve of A tell you?
It says that there is too much A to react, so we make it too fast in the batch.
Yeah, because in the end we have two rates we need to compare. That's a transformation rate by the cells, where we have added a specific amount of the cells, yeah? And then we have a feed rate of A of 24 millimole per hour. Now, if during our batch A is accumulating, what you see here, then the feed rate is not adjusted to the biotransformation rate. Or in other terms, the feed rate is too high in relation to the activity we have in this reactor. So there are two ways. We can either increase activity in the reactor, so add more cells, or can lower the feed rate. That would be the consequence. And since we wanted to increase the productivity per amount of cells, our target would be to decrease the feed rate. Okay? Now let's do this. We have now here 24 millimole per hour, and I will reduce it now to 7.2, and you see situation changes. We still have a slight accumulation of A. B is the intermediate, and C is the final product already. So just by reducing feed rate, and if we further reduce the feed rate, we come to the scenario we were expecting. Namely that we constantly produce C we have A not detectable anymore, and the intermediate B is on a very low level. So that's an ideal fat batch reaction. So you can see the influence of the feed rate is significant, and that's a point, also learning point. So independent of the bio part, of the biotech part, process engineering determines the performance of the overall systems and determines what are the points of optimization. Yeah, and with this, the productivity could be increased by a factor of 9 from starting up around 0.5, we're now to 4.5 grams of product per grams that are weight just by switching to feed rate with the appropriate rate. Okay, so this was fat batch and questioning. So the important point is if you get any result like this, you always have to analyze what is the information I have. You can ask me for information like if anything on kinetics or whatsoever. Here I don't have, we didn't have time to measure, let's say it that way. But what you see, and you see an increase of the starting material when you install the feed. The result here, the first conclusion for sure has to be that your feed is too high feed rate in relation to transformation rate, because the transformation rate you can also express as millimole per hour. Okay, I hope that point was understood, and we're moving on to the next example, and this comes out of the area of hydrolysis. The target is a pharma compound, and also here I would like to discuss with you in detail what's going on. So this is even a chemoenzymatic reaction sequence. So we're now working in no water, no organic solvent, we're working solvent-free. So we're working in the pure reagents, which are all liquid, and we do not add any salt. So we're starting up with this phenyltynamine, you can see here, and that's this chronal structure. So in the end, it's an ester and an amide, what you have to see. And this is a chemical reaction. If we heat this, we form this racemic intermediate, which is an ester and an amine. So an amino ester that's being formed. And now you already see at the waved line here and the RS indication, racemate. For the pharma product, we need to have pure enantiomer, so ideally 100% E. So how can we do this? So we apply a lipase. So that's type named Novozyme 435, but it's nothing more than a lipase. And now if you remember today's lecture, we talked about transamidation, and that is in the end what is being carried out here. So we have the amino ester. You see we have 2 equivalents of the amines to 1 equivalent of the ester. Here only 1 to 1 has reacted, so we have 1.2 equivalent left over. And these are the one, the same compound here, the leftover that was added in the beginning to do the second reaction catalyzed by the enzyme. And you can see the enzyme is catalyzing the amidation for the R amine. There you see the R amine, and that is amidated. We're splitting off ethanol here. That's what you see here. And the S enantiomer is not reacting at all. So our example we see here is a very classical kinetic resolution. Yeah, and then here it's the pharma product, which is the beta amino acid. 3 steps of downstream processing we're not discussing here in detail. Why are beta amino acids of interest? Because you know in nature mainly you have this alpha amino acids. Now these beta amino acids as pharmaceuticals often act as inhibitors for enzymes in your body, and therefore some pharma products have better amino acids contained. Yeah, that's the situation. Now we want to run this reaction sequence, which is solvent-free in just one flow, to carry out this kinetic solution, what we see here. We're just focusing on the biotransformation right now. And my question to you is, kinetic resolution for this example, what is the best reactor for this reaction sequence if we want to run it continuously? And just to remember, and then we can discuss this, we had the three fundamental types. Here in the end, we have the batch reactor. And batch reactor, we have concentration as function of time is changing, but at a given time point at every place in the reactor, we do have constant concentration. In a packed batch reactor, the time axis is replacing the length axis. So over the length of the reactor, we see consumption of the starting material and generation of the product. But at an individual point, at an individual length point at a given time, we see constant concentration over all time at one specific point. And continuous operates the tank reactor, if you remember, is operating under outflow conditions, always maximum product concentration, minimum starting material concentration, and respectively CCR operation. Now, we said we want to run the kinetic solution in a continuous manner. So you can select between packed bed reactor, so plug flow reactor operation, and continuous stirred tank reactor operation. So back to the question, what is the best reactor type for this reaction sequence or for this kinetic resolution? So I do take any answers, explanations from you, either by chat or by opening up your microphone. And by the way, we discussed this in detail already in the lecture. It's just a repetition, but on an example, like all the questions and tasks you get, just making use of your knowledge. No idea? Yeah, perfect. Fernando, I assume, generated the questionnaire just now. Is that right? Perfect, thank you. Okay, so the majority for you is for the plug flow reactor. Yeah, good to see. But the question is, who could explain why?
I think it would be because we could immobilize enzymes and use it as a packed bed reactor. And that way we could essentially bring in more enzymes into the reaction while still having a kinetic resolution.
No. It's a different explanation. Fernando, can you close the questionnaire because I cannot close it somehow? Okay, now you see the results. Well, the right answer is the plug flow reactor, the packed bed reactor. The red curve is that of the CSTR, where we get a very bad point of inactivity in terms of conversion. And the explanation is, and in the lecture we had this detail when we discussed this, the explanation is that in one residence time, we're working under outflow conditions here in the CSTR, we always add racemate to the already ongoing separation. And therefore, we're always adding the wrong enantiomer during the course, generating the outflow conditions. And this is a specific advantage, or in this case, disadvantage of the CSTR in contrast to plug corrector, because in the plug corrector, we add a volume element in the beginning here. This is filled with the enzyme, the blue rectangle. And now this volume element is running through here and is being kinetic solution is carried out, but no new racemate comes to this volume element moving up here until it exits after, let's say, 1 hour of residence time. In the CSTR, we have the volume element that enters here, flying around, twirling around for an hour, but constantly we add one-to-one racemic mixture. And so we're destroying what we're generating in terms of inactivity with the enzyme, and therefore the outcome CSTR kinetic resolution is bad. So learning point, just a repetition from the lecture, is that if you run a classical kinetic resolution, you will normally never choose CSTR, you will always go for plug flow reactor. Detailed explanation and transparency seen in the respective Biocatalysis enzyme technology lecture. Yeah, and now setting up the overall system. So the overall reaction sequence is a picture from our labs. You can see the two feeding pumps here, P1 and P2. You see the substrate reservoirs, the two. And then in here, that's the chemical reaction going on. That is the Michael addition at 80 degrees Celsius. And this is nothing more than a tube reactor where the chemical reaction is going on, 30-meter tube, swirled up and heated. And the outlet here is then fed to a packed bed reactor, or you have two in sequence, but in principle is one at a high temperature where the kinetic resolution is carried out and product being collected here in the sample collector. And you can see it's 100% conversion in view of starting material. We get a 60% conversion in view of the racemate, because the activity was just around 30, 32, and we get almost 100% EE. And this small reactor setup, continuous operation, we have a space-time yield of kilogram per liter a day, so that is even sufficient for industrial supply and operation. Yeah, so this just as an example out of the class of the hydrolases. And once again, you see, like for the exam, you just need to know the principles and see how to apply those and how to combine those. So it's really important for the examination that you think for yourself through the principles we have discussed. And those were mainly also the ones that we always had on the white or blackboard in the lecture hall or whiteboard here on the iPad that I was demonstrating you online. For the next example, we're jumping further to enzyme class 4. And this is now a little bit challenging, but it makes use of your kinetic know-how that you have gained in this lecture. Now, what is the challenge? What is the motivation of this? Well, in the end, we have two compounds that we want to have reacted. That's an aldehyde, here on the left side, benzaldehyde, and hydrogen cyanide, so HCN. If we do not have a catalyst present, so no enzyme, just bring these two compounds together in water, then we generate a one-to-one mixture racemic product of the hydroxynitrile. That's just chemical synthesis, no catalyst, just adding these two compounds in water. Okay. Next step will be we are adding enzyme class 4 oxynitrolase And this enzyme catalyzes the same reaction, but just produces one enantiomer, just produces the R product, 100% selective, almost. Now, that's a good point. The big disadvantage is you are unlucky in that sense that this chemical reaction is running in parallel the whole time if you don't control it. And now the question would be, and you can discuss re and C phase effect in view of chirality and selectivity, just to remember the chirality lecture, but we're not doing this right now here in view of time. So we're just thinking about, we do have highly selective oxynitrulase just producing the R, and depending on conditions in water, we just see the side reaction running. Now that's your point, and the question is, how can we maintain a high non-selectivity, or in other terms, how is a system we can produce just the R mandylonitrile? And this is possible because the setup is in industrial production, so there must be any ways. I won't give you any further information. You have to ask me now what you want to have for information to come to decision what you're going on. And if I have the information, I will show them to you. So what would be nice for you to know? Just go ahead and ask me. That in the end is a scenario in industry. As you get this information, and now you have some technicians, you have to give some tasks to find out what you want to know. But the question is, what do you want to know? So ask me what you want to know. I give you the results. You're a technician. I'm your technician. I will make what you want. You don't need to come up with a solution yet. You need to bring some system information, and you have to tell me what you want to know. I'm a technician, and I will show you some graphs or give you some information by explaining you something of tests I've already done, but you need to ask me what you want to know. Reaction rate. Okay, reaction rate means you want to learn something about kinetics, that's right?
Okay. Yes, I was thinking about how fast the reaction runs. So
yep.
If our non-wanted reaction runs slower than the wanted reaction.
To be honest, I do not know, but what type of experiment shall I carry out that I could show you the results that you can learn some knowledge? So I could give you, if you ask me for reaction rate, I could say the enzyme reacts with 3 units per milligram.
You can either work with the initial rate measurement, or you can do the analysis curve analysis. I don't remember the exact name.
Well, you should not explain me what I can do. You should tell me, I'm a technician, what I should do to present your results. You can judge how to proceed. So what experiment should I do for you?
I would say the analysis curve. What is the exact name?
So a kinetic analysis, yeah?
Yeah, kinetic analysis.
Okay. If you want a kinetic analysis, you get a kinetic analysis.
Okay.
One moment. Okay, this is a kinetic analysis I've run for you. And so we see here the reaction rate. We see the benzalate, that's the starting concentration of compound 1, of starting material 1. I'm sorry, but there was a problem. I had a coffee break, and when I came back, I forgot, to be honest, which was the enzyme and which was the chemical non-catalyzed reaction. But maybe you know, because you heard this lecture by Lisa, I think, at the
The top one would be the one with enzyme, because it runs like a Mika's Menten.
Yeah. Okay, good answer. That it will be. You're right. So the upper plot is the enzymatic reaction, and the lower plot is the non-enzymatic reaction. Okay. Can you get any clues out of this? How to operate, how to select?
I was thinking maybe a CSTR reaction. My reactor.
Once again?
I asked me what reactor I would choose.
Yeah, so my question is, what do you learn out of this kinetic analysis now for you, for the selection of the proper director, for the selection of reaction conditions to differentiate between enzyme and non-enzyme catalyzed reactions, so between non-selective and non-selective reaction. So what is your learning point out of the results I have presented you as technician to you now? You're sitting on the desk and you have to decide the next steps.
I can see the reaction rate is way higher for the enzymatic reaction than the non-enzymatic reaction. And so therefore I would like to run a CSTR reaction reactor where we always run with very low substrate concentration, because then we will be in the first order reaction rate constantly.
Yeah, okay. So in other terms, so it's right what you're saying. So in the end, the selectivity and the EE, enantiomeric excess, at the end of the day, is determined by the ratio of these two rates, the non-enzymatic catalyzed racemic reaction and the enzyme catalyzed reaction, or being up here. And so the difference makes up the non-selectivity of the final product. And so the highest differentiation we do have at low starting material concentrations. Low starting material concentration means highest differentiation between catalyzed and non-catalyzed. And your conclusion was totally right. The highest catalyst, so the highest differentiation we get in the CSTR operation. So your conclusion was totally right. Okay. But to be honest, it's not good enough yet to run a reactor. So we know the CSTR. We know we want to operate at a very high conversion point to have low residual starting material, to have the highest selectivity. But you still see in an unlucky manner. So even if you would start up here, let's say with 2 millimolar of benzaldehyde, yeah, you still would have a residual amount of non-enzymatic reaction to be observed. How could you still fight this? How could you still prevent this? To even more have a pronounced enzymatic biotransformation and have even less non-catalyzed reaction. What other parameters you need to know that you asked me to analyze? Okay, optimize pH and temperature. One of your colleagues is saying, absolutely right. Okay, let me show you some results. If you want me to do this, I'm your technician, I do whatever you want. And so let's start up with temperature. We see here the relative reaction rate as function of the temperature plotted in Kelvin, or up here you see Celsius. And the hollow points are the non-enzyme catalyzed reaction, and the blue points are the enzyme catalyzed. And out of this analysis, we can, by means of Arrhenius, calculate the activation energy, and we found out the non-enzymatic reaction has an activation energy of 73 kilojoule per mole, and the enzymatic reaction of 46 kilojoule per mole. So the reaction with the lower activation energy, which is the enzymatic reaction, becomes more dominant at lower temperatures. Yeah? So what temperature would you like to apply in the process?
Lower temperature.
Right, low temperature. So 10 degrees, maybe we can even allow us 5 degrees. Even down here, we have a more differentiation. And this is now adding up to the kinetic analysis that we had done. Now, second suggestion was you wanted to have a study on the pH, and asked me. So I will also give you that one. That is the pH study. And once again, the hollow points are the non-enzyme catalyzed reaction. The filled blue dots are the enzyme catalyzed reaction. The reaction rate plotted as point of pH. And you see, if we go below 4 low pH values, we have all additionally reduced the amount of the non-catalyzed, so the racemic parallel reaction, in contrast to the enzymatic biotransformation. So we know we want to have acidic conditions, we want to have low temperature, we want to have a CSTR operation that at the end of the day we have high conversion. So let's put this into operation with this knowledge. Discuss this. And this is now what the result we see now out of the continuous operation of CSTR, enantiomeric excess as function of conversion. And this is produced under these conditions here. We have a residence time, membrane, enzyme membrane reactor. We have a residence time of 10 minutes. We have a maximum conversion of 90%, an EE of 90% conversion. There we have an EE of 99%, and the productivity in this reactor is more than half a kilogram per liter a day in view of space-time yield. So you have come to the right conclusions to scale the system under such condition that you do not have significant here side reaction going on, delivering a racemic product, and just produce the real target product. Such systems are, for example, in operation by the company or nowadays Snowsen. Okay. Now, however, I'm a technician, and you know I was also playing around a little bit with residence time. And when I reduced the residence time, I observed that suddenly, well, that was what I expected, the conversion was going back, but I suddenly observed that the EE, the enantiomeric excess, is dropping with dropping conversion. Why is this? What could be the explanation in this continuous operation that if the conversion in the reactor is dropping, so from here down from 90 to 43 to 20% conversion, at the same time point, the enantiomeric excess is decreased. Why is this? Can anyone explain? You can explain it with all the results we together have generated now. Is it unreacted substrate? Well, the substrate is, let me just go back. So that was our reaction. This is the unwanted racemic reaction, non-catalyzed running in water. And we had said if we reduce the pH, if we have acidic conditions, if we have low temperature, then this reaction is reduced in rate. And we select for the biotransformation just producing the amandine trial. And then we additionally had a study in the kinetics. The lady asked before, we compared the rates, which is for one catalyzed Niels-Benten plot, and the other one was just a linear correlation dependent on starting material. And because of this kinetic comparison, we decided for the CSTR to maintain benzaldehyde concentration, starting material concentration, low level. And now it's not the unreacted substrate, therefore, as answer there. This was the kinetics we had determined, where we select reactor for. And now our problem was if we operated like we had planned, everything is fine, 90% conversion, CCR, outflow condition, complete EE, almost complete EE, in range of the measurement errors, larger 99% E. But the question is, if we shorten residence time, we have a lower conversion because of less reaction time. And why is then the enantiomeric excess so significantly dropping? To give you a hint, this is the answer. Why?
There's a big variance in the data.
Sorry?
There's a very big variance in the data.
Variance, you mean here in the kinetic determination? No.
Yeah.
Yeah, there's a variance, but that's not the reason. No, it's a different point. So the starting material in discussion is a benzaldehyde, right? That was this compound, okay? Now, if overall conversion is dropping, we have a higher amount of the starting material, right? So this is the CSTR operation you can just explain with this kinetic plot. Because under CSTR outflow conditions, we had said we are operating highest differentiation here. Now, if we shorten the resonance time, in this plot, means we have less time for operation, less time for conversion. So in other terms, the product amount we're forming is dropping, and because we have less time for reaction, therefore the residual starting material is increasing as function of time. But if the starting material is increasing, we have a big problem, because if the starting material is less converted, increasing in the reactor, and that is moving from left to the right side, the differentiation between the non-catalyzed to the catalyzed here gets smaller. Yeah. And in other terms, we produce more side product, namely the other enantiomer. Yeah, that's also writing in the chat. The substrate accumulating, and then the difference between catalyzed and catalyzed is lower, right? So that's the important point. And therefore, if we run such types of reaction, we have an enzyme catalyzed product formation, and we have a racemic non-catalyzed reaction going in parallel for selection. The right reactor would be the CSTR, but we have to watch out for the conversion we establish and close control of the resonance time, because if conversion is dropping, in consequence, we have a higher amount of residual starting material, meaning that in this plot we're moving to the right side, the differentiation gets smaller between enzyme catalyzed, non-enzyme catalyzed, so we're producing more racemic side product that is destroying our enantiomeric excess here. Okay, I hope everyone understood this. If you did not understand it, that's important. Talk to your neighbors, talk to your colleagues, and explain to each other how this might function. Or look at the video overlap. Okay, and now we're coming to the last case study for today we're discussing. And this reaction sequence, once again, it's also enzyme class 4. It's an enzyme named benzaldehyde ligase. Care in detail what enzyme that is. The important message is we have two starting materials, or we have one starting material, that's benzaldehyde, but two molecules. And those two react to this intermediate that's named benzoin. And then by adding acetaldehyde, this is split up again, and we're generating 2-hydroxy-1-phenylpropanol. The problem in the system is solubility of this intermediate the two aromatic rings. And because of limited limitation solubility, we're adding DMSO, co-solvent, dimethyl sulfoxide, organic co-solvent. We're adding to increase solubility so that at least we get a solubility of this intermediate of 1.4 millimolar maximum, because the enzyme is just reacting compound. The system is of interest because we can generate this with a very high E of larger 99%, and it's also a precursor for pharmaceuticals that are being produced large scale. Now, taking a look at batch operation, we're always starting from the batch operation if we are cases. So you see here plotted concentration as function of time. And it's typical like in the first example where today reaction sequence 1, 2, 3 or A, B, C. So in blue, benzaldehyde starting material is decreasing with time. Then we have the intermediate benzoin in green, this compound being formed and decreasing with time. And then we see finally the final product, dihydroxyphenylpropanone, this one, orange, looks ideal in the batch. No problem at all, everything is fine. Now, since the batch is running so nicely and we're thinking we want to produce more, we want to make more use of the Biocatalysis, we decide to go for plug reactor. So bed reactor, enzyme being immobilized. So such reactor is set up in the lab. Packed bed chromatographic column where the enzyme immobilized particles are packed into, started, and everything looks great. Technician goes to the coffee break after starting up because it was clear it was running without any question, and then comes jumping back to your office after the coffee break, just being very shortly in the lab because suddenly this column looks like this. So this bluish color that was before he went to the coffee break, the whole column, that's the immobilized enzyme. And when he returned, pressure was up, and so here at the inlet, color has changed significantly to white color in the first third of the reactor, first quarter. What is the problem? Any idea? The answer you have on this transparency. Everything.
Accumulation of the intermediate.
Where and why?
In the start column, because that's where we have a high concentration. This is the first product that we will get formed, and it has a max solubility that is quite low.
Yeah, so Christoph writes in the chat, guessing out of side product. No, we don't have any guessing. It's a closed system. Correct, so there's no guessing out. But what Emily is saying is right. It's a problem with intermediate, because if you take a closer look, maximum solubility I've given you 1.4 millimolar. If you look at this plot, even if it's small, here we have concentration of 5. This must be concentration 2.5. And the intermediate, the green one here, the benzene, is 2.5. So we're exceeding solubility. So what you see, since the time resolution here in this batch is the place solution in this reactor, and we have inlet from top to bottom. So this first third where we're exceeding the solubility limit will be here where my red dot is 1.4. So this is 2. So solubility limit is here. It's exactly this length of the reactor we see here, where this one is crushing out, blocking the column, and yeah, it's blocked. Yeah, what can we do? How can we overcome this?
We need to start a recycle stream.
Right. So we're inserting a recycle stream, P1 to P2. We said 20 times faster you need to be to establish a recycle stream. So we have 2 pumps. One is feeding from the top to the reactor. Second pump will generate a recycle stream over the pump. And now if we are operating this was a starting solution, we can move with the same reactor. We did not disassemble this, just adding up the pump, the recycle stream in the ongoing process, switching it on, and you can see we can run into a constant steady state operation, which then can be continued, just the unstable change to this constant operation point. We see benzene as a low concentration, benzaldehyde, so starting material intermediate, very low concentration, final product at max concentration. Outflow conditions once
again. Can I ask a question?
Yeah, sure.
This is more exam related because the question is what is the appropriate reactor for continuous synthesis? And you show the problem of the PBR. And I know you're saying run in CSTR mode, but I think I will probably just answer CSTR. Would that also be an appropriate answer for this type of question?
Yes, the CSTR mode is the right answer to operate, yeah.
Yeah, but what if I just said a CSTR tank?
Once again?
What if I just said a CSTR tank?
Well, you could also apply a CSTR tank reactor. That would be the same than this one. But since we're working with the immobilized enzyme and we already have the immobilized enzyme in this column, easiest is not to unpack the reactor, desorb the enzyme to establish CSTR in a still tank reactor. Yeah.
Okay.
Because you're working with the immobilization in the still tank reactor, you have this problem with the diffusion limitation because of no convective flux on the surface of the particle.
Right.
So
thank you.
It would be better to operate it like this with immobilized enzyme. Okay. Did this answer your question?
Yes, it does.
Okay, thank you. So then there's still a question in the chat. Why does this lower the concentration of benzene? Why does this lower the concentration of the benzene? Because we're operating under outflow condition. And we're always also in the sequence, like what we've seen in the first example today, with selecting for the final product. So starting material and intermediate will be lower concentration range. Okay, that's a specific property of the CSTR. Here it is drawn as the tank reactor. Alternatively, is what we've just seen is the expert reactor, but with the circulation loop. So here. Okay. Yeah. With this, we're at the end of this case studies for discussion today, and in part repetition of the technical biocatalysis lecture. So do you still have any questions I can answer? Okay, don't see any. So you have more examples in the PDF file to this lecture today, where you can also just see if you can follow those. Feel free to contact Fernando or myself if you still have questions via email. And before we finalize today, I would like to share with you a Mentimeter evaluation of the two lectures. It would be great if, since there's no official evaluation of the lectures this year from the THA, it would be great if you would give me some feedback here. So the first slide goes to Biocatalysis enzyme technology, the second one to technical biocatalysis lecture, and you need to go to menti.com, and the code for today is 1475512. It would be great if you would give some feedback still here. I'm just waiting that some more of you sign in, and then I will go to the next transparency. So that is the first lecture on Tuesday, Biocatalysis and technology. And then you get the same questions for this lecture, technical biocatalysis. And then you have the chance to give some open feedback. Yeah, but it's nice to see that seems to be that you like the lecture, even in the digital format. However, I know the format in present is much better, especially like things we do today where we need to have a discussion where just questions or open answers can be discussed in the auditorium or invitation and lectures. Yeah, thank you very much for the feedback. Then I would like to skip to the next one. This is now for the technical biocatalysis lecture. Would you judge this differently, the one as of today? Yeah, thank you for the feedback. Also here, I can see that there's less positive in terms of I could follow and understand all explanations. I know this is also the little bit harder part to follow, and you have more principles in mind to judge all this. But yeah, thank you very much for the positive feedback also here. And then you still have the chance to just transport some thoughts you have or something I could optimize in the next round of lectures. So feel free to anonymously also give some feedback here. Okay, I don't see any further feedback. Then I thank you very much for joining my lecture. And yeah, I wish you a lot of success for the examination. If there's any pressing matter, feel free to contact Fernando or myself for questions next week. Yeah, a lot of success, stay healthy, and see you around at the tutor. Thank you very much. Bye-bye.
Bye-bye. Thank you.